Let's look at exercise 2. Here we're trying to prove that if n is a positive integer such that n mod 4 equals 2 or 3, then n is not a perfect square. You may not be familiar with this term mod. Means modular arithmetic, and essentially it's simply the remainder when you divide by 4. So what we're saying here is if n is a positive integer such that the remainder when you divide n by 4 is 2 or 3, then n must not be a perfect square, and that's what we're asked to prove. And that's not an obvious thing to prove. So let's look at how we might go about doing that. What we notice to start out with is we've got multiple cases here in the hypothesis. We're looking at n mod 4 equaling 2 or 3, and because of that, that's going to mean more work for us. We have multiple cases to prove. It may be easier if we can frame this proof in another way that has fewer cases. It might make it easier on us. And so that's the motivation for using the contrapositive in this case. So let's look at the contrapositive. The contrapositive would be that if n is a perfect square, then n mod 4 is 0 or 1. Just take a look, make sure you understand why that is the contrapositive of this statement. We're taking the conclusion of the original statement, n is not a perfect square, and we're negating that, so n is a perfect square, and we're making that the hypothesis. Now we look at the original hypothesis, n mod 4 equals 2 or 3. Well, the negation of that would be that n mod 4 does not equal 2 or 3. But when we are dividing by 4, the possible remainders are 0, 1, 2, or 3. And so it's equivalent to say that n mod 4 is 0 or 1 when we say that n mod 4 is not 2 or 3. Okay, so we say n is a perfect square, and we can use that as a single case to start with when we look at proving the contrapositive here. Now we want to move to definitions and write things mathematically. Think about how you would write n is a perfect square in symbols. I would write that as n equals a squared, where a is an element of the integers. But moving on from here, it's not obvious how to proceed. How can we move from a squared to showing that that number divided by 4 leaves a remainder of 0 or 1? We need to think about what kinds of squares exist, and therefore what kind of numbers a can be. And this is what's not obvious, and we need to sort of make sure that we hit all the possibilities. So what kind of numbers can a be? And we think about the number 4, right? We've done some proofs earlier regarding evens and odds, and we look at a and we notice that a can be either even or odd, and that does affect its remainder when dividing by 4. So we do end up with multiple cases here, 2 cases in this problem, even though we tried to avoid that at the beginning. The first case is that a is even. And if a is even, we're going to write that again as a equaling a multiple of 2, k standing in for that multiple. And we notice right away the relationship between the squaring and the number 4. If a is even, if a is 2k, then a squared, of course, is 4k squared. And we see, oh, a squared is a multiple of 4. And if a squared is a multiple of 4, then n is a multiple of 4, leaving a remainder of 0. And so if a is even, we definitely have the case where n mod 4 will be 0. So right there, half of the perfect squares are going to have a remainder of 0 when we divide by 4. Okay. What about the odd case? What about when a is odd? Well, if a is odd, we're going to write that as a equals 2k plus 1. Again, here I'm reusing k because I'm treating that as a separate proof, right? So we've talked earlier about when it's appropriate to use different values of variable, or excuse me, with different variables to represent our values. In this case, I'm reusing the variable k. Basically, it's a new variable k unrelated to this case. In this case, if we have a is equal to 2k plus 1, then a squared is that quantity squared, which is 4k squared plus 4k plus 1. And we can see that the first two terms here have a factor of 4. If we factor that out, we see that a squared is 4 times the quantity k squared plus k, and then plus 1. And since 4 times the quantity k squared plus k plus 1 is 1 more than a multiple of 4, it's going to leave a remainder of 1 when divided by 4. And so a squared mod 4 is equal to 1 when a is odd. What we have to be careful of now, and it's obvious in this case, but not always, is that we've hit all the possibilities for a. Can a be anything other than even or odd? Well, no. All integers are either even or odd. And so we've covered all the possible squares. So if n is a perfect square, it's the square of an even number or an odd number. And so we've covered all perfect squares and shown that for any perfect square, that square mod 4 is either 0 or 1. And so we've proven our contrapositive. Sometimes it's easy to miss a case and leave an incomplete proof. For instance, you might have a proof of integers where you forget about the number 0. You show something for negative values and positive values, but you forget 0, and then you have an incomplete proof. So it's something to watch out for as you're dealing with cases, proofs with multiple cases, making sure that your coverage of the entire set that you're working with is complete. But in this case, it is complete because a must be either even or odd, and as I said before, we've shown that a squared mod 4 must then equal 0 or 1. And our original statement that n is a positive integer such that n mod 4 is 2 or 3 means that n is not a perfect square is also true because of the logical equivalency of the contrapositive.